Howdy, everybody. We're here for the finale of Everybody Codes 2025, Quest 20. I don't know why I blinked there. My apologies. We're at the end. Maybe that's why I blinked. Because I think it was a great year for Everybody Codes. I had a lot of fun. Thought they were good puzzles. This one was good as well. Should we even maybe just look at my times? I think I showed my times. The part 3 required some thinking. It actually wasn't as hard, so I suspect this wasn't quite as crazy. I think my times might have actually been better. I actually got 61st place, but I think my times might have been better because I had a few interruptions. I'm doing this on like Black Friday here in the United States, where we all go do all of our shopping. I don't like to do it, but we do look online for stuff. Kind of doing some stuff in between, also prepping for stuff. It was a little off, but the gist was, maybe I'd read the problem, have to think about some stuff. I'd go do some stuff while I was, but it still was a good day. Very interesting for me. I had a lot of fun. So let's just get right into it. So what happens is you've now finally flown through your Flappy Birds thing, and you've reached this crazy new area, like the final zone, and you land on a triangular grid, is what it is. Land on a triangular grid. And it happens to be that there's trampolines on the triangular grid, and then there's void around it. So the T's represent trampolines and the hashes represent. They give it to you in a text format, so you can like parse it. But just to be clear, like the text format doesn't represent the actual grid. Again, because the rows alternate, right? If you think about where I think the way I did it in the puzzle is where the edge is that could be like attached to something. Like it's up here, it's down here, it's up here, it's down here. And so even though like on this grid it looks like these two right here, this one and this one, could be connected to each other, they actually aren't in real life, right? They don't share a grid. So like you can see, that's this T right here and this T right here. The ones next to them do, though, because they share an edge. That is, this one's facing down and that one's facing up. So that's and it basically says, because your wings are tired but your legs aren't, you're going to use the trampolines to jump around. Before you do that, for part 1, you need to figure out which ones are connected. And the gist of it is can you kind of figure out this triangular logic? That is to say, can you find this one is connected to this one's connected to this one is connected to this one, and so on and so I guess I could try and draw this, right? Like the thing that you're looking for is like for part 1, you're looking for these connections. You're looking for these. So this one's connected, this one's connected. These two are not, but this one is, this one, and so on and so forth. So that's what you're looking for. You're able to jump from adjacent ones. So you obviously need to know which ones are adjacent. And that is to say, you could jump from here to here to here to here. So like this would be a path that you could take. You could go from here to here to here, but you could not go down. That makes sense. And so that's what part 1 wants you to do, is can you find them? So I think the hardest part of part 1, and what took me a little bit of time, was just trying to figure out how to represent this properly. And the way that made most sense to me, because I've done a little bit of this stuff in like have you ever played games that have like hexagonal grids? And it works similar to this, right? Is like in a normal 2D grid, it's very easy to say, oh, I can go up, down, left, or right. But in like a triangular or a hexagonal grid, you now have other ways, right? So this point right here, the way to think about it is you could travel here, you could travel here, or you could travel here, but nowhere else, right? Because there's 3 edges to the triangle, there's 3 possible paths. A grid has 4, right? And so like that's the difference is with a grid, you can go 4 directions. With a triangle, you can only go 3. So how do you represent that and how do you show that? And so I'll just okay. So this what is part 1 saying? Take your triangle and find all the connections, and then return the total number of pairs. So in this example, there's 7, which I think I showed most, if not all of them. Right? These ones are connected, so you have a total of 7 pairs. So what does that look like in code? Well, I wanted to track a couple things for this because it felt clear that we were going to be working with this triangular grid. So I wanted to make sure I set it up correctly. And up until part 3, like the math is pretty easy. And so that's what I did. So here's what it is for part 1. You need to know what type of cell it is. Is it trampoline or empty? Obviously, if it's empty, you can't go to it. If it's a trampoline, then you can, right? I think they actually call this the void. So you can't go in the void. And then I just need to know where my edge is. Is it above me or below? Is it up or down? I guess is the way to think about it, right? And so that's this part right here, right? So this in this one, this is up, and in this one, this is down. And if you notice, it actually alternates, and so that'll make sense in a second. But you start every row with it being up, and then goes down, up, down, and so on and so on. And it does that every single day in this triangle. If the grid was oriented the other way, it would be the opposite direction. The math would change a little bit, but largely this. I mean, okay, so now we just need a cell or a triangle, I guess. They called it a cell in the program or in the puzzle, so I called it a cell. So I need to know what type it is. Is it, excuse me, is it a trampoline or is it empty? And then I need to know where my edge is it up or down? And so I created a new function. You give me a character and a direction, and I'll create myself, right? And then I just need my grid, right? I need that grid to be built up. So there is some logic here that is like I think is important. I think you don't have to do this, but for me it felt easier to say all of these rows start at position 0. And you'll see why especially in part 3 when we have to do rotations. But the reason I want to do that is because it makes the logic fairly easy. Like I know if my direction is I can go up here, like I can easily I can easily find this position up is the way to think about it. But if I've started here, it's a little bit different because there could be a couple here, a couple there, and yeah, I think you had to do some. You might still be able to do it, but you kind of have to do some extra math to remove this section of it as you're doing your counting. So it was easier for me just to do it this way. I think we'll see it was, but at least for me, it felt like that was easy. Okay, so what we need to do then is just can we build our grid? Ignore the start, end, and rotate. Those are for parts 2 and part 3. What we're really interested in is can we build our cell? And that's not actually not that hard, right? You just start at 0. I think this is you could actually enumerate this now. The reason this is the wrong way is because I may have been starting at 1 when I was initially solving the problem. So this is weird. I apologize. It's not very idiomatic Rust to do that. I may go back and fix that. But basically, we're going to take, our lines. Excuse me. We're going to enumerate them. And then we're going to, for each of our lines, we're going to iterate through them, right? The one thing I'm going to do is you can see, notice like I zip this 0 with this, but I skip my row count and I take until I get to a dot. or while I have a dot, and that has the effect of like removing these dots, right? So at row 0 I don't remove any, at row 1 I remove this, and I take until I get to this, and that has the effect of I'm only getting these, and this starts at 0. So I think I can change this. Maybe I'll try it real quick. When I had started I couldn't. Lines this, and yeah, gets us to the same. Okay, so I had switched those, I think, because when I was doing some math earlier, I thought maybe I could do one's it would be like one's logic, if that makes sense. I would start at 1, but it turned out he was easy to start at, because what was happening is I was -1. That makes you -1 fewer time. But basically, I go through all my lines, then I go through all my characters, and then this is the part that's saying skip the dots along the edges, and then I zip with up and down cycled. So this is giving me my direction. I always start up and then I go down, then up, down, up, down, up, back and forth, back and forth. So this is a cool way to like do that throughout the row, because you start it up and then you go down and then you intercycle. And this is where I'm saying that I think this part makes this logic easier, because it would change whether you start up, down versus down, up, is all. If you weren't doing this, you'd have to figure out, you wouldn't start zipping until you wouldn't start using this until you'd reach the first actual triangle. So that's why I did it this way. So once I have that, I now have my row, my column, my up, down, and the character. So this is giving me my start and end positions. Again, we can ignore that. I mean, maybe I can just tell you right now. Later, you have a start and end, and you're actually going to traverse. And so I'm looking for an S and an E, and if I do that, I have my start in. Otherwise, I just create my cell, and then I collect each row, and then I collect each column. I collect each column in that row, and I collect all the rows, and that gives me my whole. So that's my create a grid from nothing. So now I have this in memory. It looks like this. How do I find these? Well, I think the easiest thing to think about here is to say, is like, I can actually just traverse these and figure out if they're connected to anything, right? So if I'm traversing them, obviously I need to, if my neighbor is 1, so I need to check my neighbor. So I check my neighbor. If that's 1, I'm good. But also if my edge is down, I should then also check if below. And those are just the 2 cases. I can literally just iterate through this whole thing and just say, is my neighbor and is my below? And once I've done that, I will have gone through all the grid and found them. And the cool thing about this is it kind of help if you know you're iterating this way, left to right and top to down, you know that you only have to check this way, and then you'll get the whole list. You don't have to worry about deduping or anything like that. So what does that look like for part 1? Well, we just say find the adjacent trampolines. So we enumerate through all the rows. Through all the rows. We don't take the last row, right? Because obviously the last row won't have anything next to it or below it. Like, you can visualize this right here. This is the last row, right? Even if this was the T, that it would have nothing this way, right? And it would have nothing. We'll skip that one. That makes the math easier too, because we know we can always go this way and this way. So how do we do that? We say, well, I'm going to create tuple windows from my row. So I'm going to now be getting pairs, right? I'm going to be getting these 2, and then these 2, another row and another column. I'll be getting these 2, and then I'll be getting these 2, two. So when I'm doing these two right here, I can just say, hey, are they both trampolines? And if they are, yes, right? But these other ones are not, right? No. So I get one yes in this one. And then you just do the same thing looking down, but you just do it with your current one, right? So if I'm consulting these two pairs, it's a yes this way, right? But it's also a yes this way. So I just need to count. And that's what this does, right? I filter by cells that are empty, but I create tuple windows. And so when I map, I have my column, my cell, and my next, right? So obviously, if my next is a trampoline and I'm a trampoline because I've already filtered myself out if I'm not, then I have an adjacent pair, right? And then if my edge is down and the one below me is a trampoline and its edge is up, which it should be because my edge is down, this is just like I think you technically don't need to do this check because it will always be correct. That this is like just clear what you're doing, right? You want this one to be down, this one to be up, and and then you want your trampoline. You want that one below you to be a trampoline. If that's the case, then that's adjacent as well. So now you've created all your adjacencies, you sum them up, and that gives you the answer to part. The thing that is like you just have to think about is like, well, what if I'm down, if my edge is down, what is the one below me? And this is obviously you're going to go to the next row, but what is the one below me? It's not your current position, it's your previous position, right? It's the previous one. Because remember, the next one, the next column is shrunk down one size. And so its 0 is shifted 1. And so your down is actually a previous one. And this is where like the triangles and I think this doesn't actually happen this way for the hexagonals, but because it kind of does, right? The hexagonals are a similar thing, right? Because they look like at least and I'm drawing terribly, but they look like this, and so they have like, you go this way, this way, this way is like the thing to think about, and so you now have 6 ways that you have to think about, and then like this one overlaps like right here, and I'm drawing this here, and so like you can go from here to here like this in 2 moves, right? Or you can go there in 1. Anyway, the triangle is much more simplified than the hexagon. I drew that hexagon, not making sense. But the idea is your positions actually change. So even if you're in like a quote unquote row when you're going down, like that's actually shifting, or I should say a column. If you're in a column, that column is actually shifting as you're going down. And you can kind of see that, right? Like if you imagine this column right, let's draw one. You imagine this column right here, like the column numbers are going to change, right? So this is 9, this one would be 8, and this one would be 7, right? So even though they kind of feel like they're along the thing, their columns are actually different. And that math is like important later for part 2 and part 3. But because I'd worked with these things before, I kind of knew, I think this is what I have to do. And so I kind of did this to begin with. I think that's why it took a little bit longer to solve this. Tried to build this up instead of underthinking of it. Excuse me. Okay, so I have my parse thing for my template. I probably actually don't need this because I can just call it grid input. But what do is for part 1, I just say, okay, parse it and give me the adjacent. That gives me my number, right? Not too hard, nothing too crazy about this one. I think that's it for part 1. A lot of it, again, we went through a lot of this, but that was to set up, can we find the adjacent What are the adjacent ones? And if you've set up your triangle correctly, it makes part 2 and part 3 substantially easier. At least for me, it did. So we'll see. So what happens in part 2? Well, it now says, okay, well, now we're going to give you a start and an end position, and we want you to find the shortest path, right? You're now going to jump from adjacent trampoline, but you have to find a path from the start to the end. So what is the shortest path from the start? And in this example, this is the shortest path. It's possible that like you may think, oh, I can go this way, but like you actually can't go this way because this one is not connected to this one. And so, this one is connected to this one and is connected to this one. That makes sense. So like this one is edges down and this one edges up. So you can't actually take this path. Whereas if you were in a 2D grid, you could totally take this path. And in fact, it would most likely. So that's what it's saying. Can you find the shortest path? Well, we know what the shortest path is. It's a BFS or Dijkstra. In this case, because the distance is 1, it's just a BFS. So how do we solve a Dijkstra type thing, the shortest path type problem? We've talked about this probably ad nauseum. We need to know where we start. We need to know if we've reached the end, and we need to know what are our neighbors. And that's the part here that is like the tricky part that you have to work through is what are our neighbors. You can ignore this note for part 3, but what we're doing is we're just calculating our neighbors for part 2, right? So we start with an empty neighbor list. I could not find a good way to do this in like a functional way because you just kind of have to ignore this or rotate 2. This will be for part. We just need to check if we can go left. And the only check we have to do is, are we at the edge, right? We obviously, we have no left if we're right here, right? So if we're on this node, we obviously can't go this way, right? That's not and that new place has to be a trampoline, right? So if that's not a trampoline, we can't go there. But if both of those are met, we can go left. Right is the same, just in the opposite direction, right? So if we're on this node right here, we obviously can't go right. That doesn't do us any. Now we check our ups and downs, right? And these are the same, but in the opposite direction, right? If our edge is facing up, we know we can move up. Remember, it's a triangle, so we can only go 3 directions. We know we can always go right or left. And then the question is, can we go up or down? So if we can go up, or if our edge is up, that means we have the potential to go up. We just need to check to make sure we aren't at the top row. And we aren't on the edge, so we couldn't go up. So like, what is that check? So obviously we can't go on the top row. What is that check doing? You actually need to do this? I think you do. Oh, this might have been like at the time I was doing eye sizes. Yeah, you don't. I don't think you have to. You just have to check to make sure you're not at the edge and that the thing above you, if your edge is up, is a trampoline. And we've already done that before, right? So whereas when we are looking down below, we're now looking up. So where we are in the column is actually 1 greater, right? So in this case, when we're looking up, it's at position 3. So our one above us is 4, right? So this is the one we'd be consulting. So maybe to clarify this a bit more, if we are consulting this node, we know the ones we can look at are down because its edge is here. And then we can always look left or right, assuming we aren't on the edge. Like that's what we're doing. I think that was because I think those 2 previous checks where I was using eye sizes. And so I was like doing some math wise things that I don't have to. after I had like solved part 3, I went back and looked at it. I'm like, oh, I don't actually have to use eye sizes because I'll never actually go off the grid as long as I make sure I'm greater than 0 and less than. And again, that's the up and down check. The down is just the opposite, right? I just need to make sure I'm not at the edge and that the one above me or the one below me is a trampoline as well. And if it is, I can push. So I will have been able to potentially push 3 things to get me to where I'm at, or to get my neighbor's list. Okay, and then once I've done that, I can just do a BFS, right? So we've done this a million times. We have our frontier. We start at the start, and we say our distance is 0. Then we have our scene list, which is our start position. This is going to prevent us from backtracking. And then we just loop through our frontier, right? If we ever reach the end, we know we're done, so we can return that cost. If we have, otherwise, we go through our list of neighbors for our current position. And if we haven't seen it before, we add it to our list of to-do work at the end. Remember, we're doing a BFS, so we always want to pull from the front and pop from the back. It's like a first in, first out, right? As opposed to last in, first out. It's not a stack, it's a queue, essentially what we're creating, right? And so we just, again, push it to the back, and we know the cost is +1. Keep doing that until we reach the end. Hopefully we don't get unreachable. That would mean the puzzle was unsolved. But in Rust, we have to turn something. Yeah, that's it. So what do we do for part 2 is we just parse the grid and we do the BFS. That will return the count, and we're done. So that's part 2. Again, I don't think this was... Yeah, I only spent 6 minutes doing that, because once you understand like the way the triangle works, the neighbors is fairly easy. You always know you can go left or right, and then you just have to decide, is my neighbor up or down, and are those 3 possible positions trampolines, meaning I could... Okay, so what happens in part 3? Well, this one took me for quite a whirl. But I don't think it was... I think I understood the problem. I just didn't understand the math, and it took me a while to figure out the math. And it's still a little fuzzy I understand it like intuitively how it works, but it's fuzzy enough that I don't know how well I'll be able to explain this, so we'll give it a try. Basically what it says is, all of a sudden you're put on a new grid that is rotating, and every time you jump, the grid rotates 120 degrees. The whole grid rotates 120 degrees. So they kind of give you an example of that. Like if you were to stand at position 1 and you jumped, you would now be at position 3. And then if you didn't move, you just jumped straight up and you fell back down, you'd go from position 1 to position 3. And then if you jumped again, you would be at position 2. And then if you jumped again after that, it would put you back at position 1. You'd be back where it is. So the grid rotates 120 degrees clockwise each time. So it starts here, you rotate, rotate, rotate. So if you just jump straight up, you would go from 1 to 2. These positions right here, the corners is the way to think about it. You go from this corner to this corner to this corner. And so they actually have this cool little graphic. I stared at this for a little while as I was trying to like solve... Well, I was actually staring at this part to try and do math, but can you see the little dragon jumping up the whole time? That little dragon got annoying because I was staring at this grid trying to figure it out, and you just see that thing keep bopping up and down, and you're like, man, that dragon is going to pay. But that's all the changes between part 1 and part 2 is now every time you move, the whole grid rotates. And so the question is, given that grid, what is the shortest path? So it walks you through that, but that's the only thing that changed, is you're now going to rotate the whole grid 120 degrees clockwise every time you make a move. Okay, My initial thought was, okay, well, do I just store the whole grid as Dijkstra and then try and, you know, my move is rotate the whole grid, and now I have a new position. Now I find my moves, and then I try and do that, right? That doesn't quite work because, like, what actually happens is, again, remember, when you're jumping, the whole grid is moving. So if you were to jump and you were to move to this position right here, so instead of just jumping straight up and down, which by the way is a valid move, that's what you have to think about, and I'll show you in a second. If you don't include the I don't move, it does not solve it may not solve. It didn't solve for my imp. So when you're jumping, if you're jumping from this position to this position, remember the whole thing is rotated 120 degrees. So when you land, you're actually landing right here. And this was the key insight, is I thought, oh, you know what that means? I actually just need to rotate myself. I don't have to rotate the grid. I just rotate myself counterclockwise each time. And it turns out that there is a known way to do this. And because I had done some stuff before, I went and looked it up. Barycentric coordinate system. So, like, what is this saying is, like, when you're on a triangle of points, you can think about like where you are on that grid as like how far you are from like the center, and then rotate around that. And intuitively, this probably will make sense, like the way to think about it. You already kind of saw it, right? Is like when you're on the edge, if you think about translating yourself from the center. So I think in this grid, the center is center's like right here. Is that right? No, I think this one is, yeah, no, this is the center right here. It doesn't look like it's the center, but it like, now I'm gonna have to, it's this that's the center. Yeah, it's actually this. It doesn't look like it's the center, but it is the center. And I know that's confusing. Why do I say it's the center? Is because if you draw a line from here to here, and a line from here to here, and a line from here to here, like those lines are equidistant. And I know, again, I know it doesn't look like that, but because of the way the triangle is built with triangles, like this is the center. And so the way you need to think about your rotation is you're just moving values that are along this part of it, like along this area right here. How do I describe this? Yeah, you're moving values that are like that, like there's a quadrant here, there's a quadrant here, and there's a quadrant here, right? And you're just moving these ones over to here, and these ones over to here, and then these ones over to here. And so that was the intuition for me, is to say, oh, I actually don't need to move the grid. I just need to move myself. And that's why I have in my code, I have this, should I rotate every time I get my neighbor's function? That's what this rotate bool is for. If it's turned on, I'm going to rotate before I do it. Otherwise, the code does not change at all. And I'll show you right here. It's just, this is the code right here. It just says, if I'm rotating, I take my row and my column and I rotate myself. And because I'm rotating, this is like kind of a special case for this problem. But because I'm rotating, I now check if I landed on a trampoline. And if I did, that could be a potential place that I stay. And in fact, it has to be, this has to be here, right? Like if I turn this off, like it won't solve. You can see like it actually doesn't solve part 3. I get to my unreachable code. And it happens to be because for my puzzle input, maybe not everyone's, but for mine, one of the solutions is to rotate it or you rotate yourself, which is what I'm doing, and landing on another place that's a trampoline, but not moving to an invalid spot, and then jumping again and rotating to put me in another place, and then I can move. Like, the way to think about it is the jumping has the effect of like getting you to places where you may not be able to go, but makes it faster to get there than if you did. And I don't know if this grid illustrates it, but you can imagine if you were like in this position and it rotated you to here, you may want to go here, but say this was a hash, you may want to go here because it's faster to get to here, which is where the end was. Like, imagine this was the end, and so it going from here to here is faster than like going from here then jumping to say I don't know, it would jump you like maybe here, but from here you have to go to here, and then from here then you can jump to there. Does that make sense? I hope that makes sense. There's definitely cases where you say, oh, it's faster to like jump from thing. So what, and so that's the only thing that changes. In fact, if you look at the logic between part 2 and part 3, the only thing that changes is I say turn on rotating and then do the same BFF, literally the same BSF function. So here's part 2 and here's part 3. So the only thing you had to figure out is this middle part, and that is, how do you do the rotation? And it's, if you look at it, it's only 5 lines of code, but it boggles my mind. And I still, it's a little hard, but you can grok it from if you understand enough about these barycentric coordinate system. I don't. I knew they existed only vaguely. In fact, I didn't even remember the name. I had to do some Googling to like find it. But the notion behind it is that you, and it's the same thing with these with the hexagonal grids or any other grid system that's not a 2D system. Like, the way to think about it is like how are you in, especially when you're doing translations, like in a maybe the way to think about this is in like a 2D grid, it's really easy to do a translation, right? If you're on a 2D grid, because like you're right here, you're literally just like moving your X and Y's, like whatever if you're translating this way, or if you're translating this way, you know, it's literally just like this, right? Because this is like a 3D grid, it looks a little bit different, and so the math is a bit fuzzy. But the gist of it, the way to think about it, at least the way that is intuitive, is when you're going from this quadrant to this, and it's not a quadrant, trident. I have no idea how. Trirent. I have no idea. So I'm just going to call it a quadrant. Someone can tell me what it actually is. To this one, you're going to maintain the same column. You're just going to change your row, right? So you're going to maintain the same column. You're just going to change your row. So notice, like, if you think about the columns as like going this way, you're maintaining the same column. You just change your row. And what is the difference? Well, if you've gone 2 this way, you just now need to go 2 this way. If you've gone 0 this way, well, now you just go 0 this way, and that puts you here, right? And that actually works for that way. If you're going from this area to this area, for some reason now I don't want to say quadrant. If you're going from this area to this area, well, you still want to maintain this line right here, right? But now you're going at it from this direction. So you're going this way, right? So this one, what does this translate to? Well, you're still on this line, but you're now going 1, 2, 3. So you go 1, 2, 3, and that's this position there. So that's how to go this way. So now that we've got the 3, you can kind of like visualize them, and you can see why this is the center point right here, because all of the rotations are happening around that point. And so when you're moving 120 degrees, that's where the rotations occur. This one is a little bit harder, and the reason I say that is because when you're notice how like the way I was describing it is you're going along these lines. Well, these lines actually, if you look at them, they're traversing multiple rows, right? So you say, oh well, there's 1, 2, 3, 4, 5, 6 rows, but I'm actually counting. If I'm counting, I'm doing like 2 from this one, and then 2 from this one, and then 2 from this one, and then 2 from this one, 2 from this one. So I'm doubling those effects, right? It doesn't look like it because like the actual row is 1, 2, 3, 4, 5, 6. Because I'm only like worried about these edges, not these points. But this like grid of them is like treated as one. It doesn't look like that though when you're on these diagonal, right? It doesn't really look like it because you're only the way you think about it, if you're thinking about it in a 2D space, these two are only 2 rows apart, right? The difference between these is 2 rows. Well, that doubles when you're up here, right? The distance between these is now 2 times 2 plus 1. And so that's the math you have to do to get from here to here. So you see it, and that's correct, right? 1, no, 0, 1, 2, 6, 4 plus. Oh, it may be like it's 3 minus 1 times is like the way to think about it. I think that's what it is. Not this one. It's this one. Anyway, so that's the way to think about it, is like that's how you're calculating. Oh, it's not actually this way. It's like 8 minus 5 minus 1. I actually don't know what this is. 3. So it's like 9 minus 8, something like that. That's not it. I don't remember exactly what. Oh, it's a remainder. Man, I'll have to go look. But that I think, yeah, so I'm not going to get the math right, and I apologize. But I think the idea is, remember that you're kind of working along these like lines, and those lines, when you're going this way and when you're going this way, they kind of you're actually counting 2 as you're going through them. But when you're going this way, you aren't counting 2. Oh, that's actually what it is. It's this one is just 9. No, sorry. It's whatever this is, 0, 1, 2. So it's 2, 3, 4, 5, 6. 6. So this one is just 6 minus 2, which is 4. So you're just going to move 4, right? But I think what it is like 9 minus 6 minus 2 plus 1 or whatever, and that gets you from here to here. It's this one that's trickier because you're only technically moving 2 rows, but you're moving 1, 2, 3, 4 things, and that's where like the 2 times whatever. You'll see the math in a second. I'll show it to you. That's what you have to figure out. And again, I got a lot of help here, so I'm just gonna post the Wikipedia. But essentially, what do you do is, well, you need to calculate your new row and your new column. The new column is the easiest. Again, like I said, is you just take your row, and if it's a multiple, if the column is the multiple of 2, it's just double the new row. Otherwise, it's double the new row plus 1. And again, I don't know if I explained that really well, but that's the difference between like this and this versus this. But then your new row, no, sorry. This is the one where if you're it's like from this to this is what you have to think about. So you're either doubling it or doubling it plus 1, because it's possible that you'll have gone over. The row is the one that's kind of hard to grok, but what you're saying is get the total length, the total height, subtract your current row from it, and then subtract the column that you were in divided by 2 plus 1. But it's actually column plus 1 divided by 2, because you want a div seal is what it is. Again, all this is explained. It's actually might be a link in here. There's a link about translation. I don't remember where I found it. I had to get some help. Again, this math wasn't me. I understood the idea at a high level, but it doesn't. It's a little bit more nuanced than how I'm actually describing it, because it's harder to find if you thought about the general formula of, oh, if I'm going from up here to down here, I just do like the column minus the things, I go along this line. And then if I go from here to here, I like just follow this line. And then if I go from here, I follow that line. Like that does work, but there's some like special gotchas with like these positions, and like this position right here especially. So like this is a position that is like really interesting. Like how do you translate this one? Like if you've shifted 120 degrees, like have you shifted, where have you shifted? The way to think about it. Anyway, I'll be full and transparent. I kind of understood, well, maybe the way to describe this is, it was clear to me that if I just, instead of rotating the whole grid, I rotated myself, then I could just do the normal Dijkstra. So I just had to figure out, how do I rotate my position? I spent some time tweaking and looking at it and wasn't quite getting them all right. And so I remembered, oh, isn't there's like this weird coordinate system. And then between this Wikipedia page, and some other Googling, like I came upon these things, and this is what gets you. Um, so I'm sure there's someone that could explain this better. But like that's the gist of it. That's what part 3 is. It's just, can you translate yourself properly? And it does require work. And this is one of those days again where I just, even if we come upon another problem like this, I'm going to have to go find this code, because the math, like again, I think if you've like, hopefully I've explained it well enough, you can probably understand intuitively what's happening, but it's much harder to actually turn that into math. At least it is for me. And so I knew I was going to struggle here, so I went online and started googling for like, hey, how do you do this? And then I was like, triangular grids is what I think I searched for, and that brought me to the barycentric, which is uh, what I remembered from working with previous grid types. I think there was someone that has done a lot of work on hexagonal grids. I used to play a game that was like, that did a bunch of stuff on hexagonal, and so that's where I learned about all this stuff, and kind of toyed with like optimal routes and like that. So anyway, there you go. That was part 3. Again, part 3 is exactly part 2. You just have to know how to rotate. And for me, it was easier to think about it as rotating myself versus rotating the whole grid. Because maybe the way to think about it is you're teleporting, like Portal. You're always teleporting in a, so the grid is moving clockwise, so you're moving counterclockwise in the thing. And if you can do that, problem solved. Okay. I think we already looked at this on day 19, but we could look at our level 20 dude. We're actually done. We did it. If you're following along and you've solved it along with me, or you've solved it yourself, it's quite possible that you solved it faster than I did. Um, and as such, it's, here. Here we go. We did it. We got our old medal. We're super dragon. Solved the puzzle. It's interesting that it didn't have like an ending. Did I miss like the ending of it? Because like you do this and you solve the final puzzle, and you kind of like know you're the dragon duck, but you watch the end of Star Wars and you're like, oh, there's the whole ceremony and the hoop. Okay, my times. Again, I don't think these ones were. I mean, I did take breaks in between. The first 2 parts, though, if you think about it, they actually aren't that tough. And so a lot of this time here, I think this gap, this like, the equivalent of an hour gap, is probably pretty accurate in me trying to solve it. Because it was really, I mean, I kind of knew, oh, this is all I have to do. And I tried to do it a couple times, a couple different ways. I if you remember me talking about, like, at first I was kind of tracking like where I was I in like section 0, 1, or 2, and then I could like just rotate between 0, 1, and 2, 0, 1, 2, 2. Um, and then I would do like some, if I'm going from 0 to 1, like if I'm at 0, I know I'm going to 1, and so I need to do like the addition that along that line, and then from 1 to 2, I was doing the movement along that line. Then from 2 back to 0, I was going along this way. But I could just never get the math quite right. I suspect that would work. Again, excuse me, except for some of these like really weird ones. Like I still not quite, I don't quite understand is like where you land on this. Like if you're on this position, where do you rotate? When you rotate, I think the answer is you rotate here. I believe the answer is you rotate here and then you rotate here. Like I think that's the way it works. But I think this is the one where my math wasn't quite working out like that. Because like if you look, it's actually like going the wrong way, if that makes sense. Um these ones all look like this, right? Purple ones look like this, but then this one looks more like this, which is a little weird. And I think that's the case too for like this one right here. Though like to a lesser extent, like where does this one fall when you're rotating? I actually think you rotate to like right here and then to right here or something like that. It's like this rotation. And so there's just like, it's like part of the grid wasn't quite working. And I don't know which one, I don't know if it was exactly those ones, but it would feel like I was going the right direction. And then suddenly I jumped to the totally wrong place. And so that's where I had to look. I was just like, okay, I know there's something about this. Let me look it up and see if I can't find it. And that's what. Okay. And by the way, I did find the Discord, although I don't know how about. I like reading the Reddit because it's got like the final solutions. Maybe in the future we can like find way I can like find solutions from Discord and just have them ready so that we can look at them, because some of the Discord is just like talking about people trying to figure stuff out. The Discord is nice though because you can get updates from the moderators and stuff like that. 20 solution spotlight. We still don't have a lot. I guess that is today's solve. I'm solving both days today. Yeah, this is the walk the staircase. Oh, so I kind of want to look at this. Yeah, so we have a coordinate. I'm so bad at the new C++. Half of this doesn't what I remember. Yeah, I feel like I'm missing rotation step. It's very likely that I just apparently I need to take C++ over again. Java is the same. Wow. I do a lot of work with Java, and like when I had learned it in college 1+ years ago, it changed a lot of my comments are almost identical. Okay, that's you don't actually. I found that you don't actually have to do that if you know how to rotate from like your parts of the grid. Oh, okay. This is really interesting though. Is like they're able to like they're actually rotating the whole grid, which is kind of which is again I kind of thought that I might originally solve it that way, but I do think you can say, oh, I actually don't have to rotate the grid. I just translate myself on the grid in the opposite direction. Yeah, and even though I don't understand the other math, this math only almost looks harder, or is it? Let's think about it for a second. It's like basically what we're saying is everything over here now becomes over here. So we take this one, put it here, take this one, this, put it here, take, you reverse it and flip it on this. So yeah, actually, that's probably mathable. That's probably doable. I'm just tired. It's almost 1 o'clock in the morning, and I usually go to bed at 9. It's been a weird. Um, row plus column. Oh, this may be like, are you going up or down? Yeah. So your neighbors is obviously back and forward, but it's also like, are you going up and down? For part 3, it could be yourself too, and that might be what's happening. Yeah. Might be yourself, but you have to like filter them out based on. Yeah, so this is left and right, and this is above or below. But you had to say, like, oh, based on where I am, some of them may not be valid. So I append them to like my final candidate result. Okay. Very cool. So it does look like potentially you could do it on the 2D grid. Interesting. Maybe I did overcomplicate it, but it feels kind of elegant, my solution, even though I had to get help with the math. All parts use parity checks for vertical movement. Part 3, 3D PFS, where the possible. Oh, that's actually a very cool idea. Just do a 3D thing in the grid, and so you have like 3 versions of the grid, and you're just going from rotating between the 3. That's a cool idea. That's very fun. I like that. And that seems very intuitive, right? Because the grid's only going to ever be in like 3 states. So if you just maintain those 3 states and see where you are in those 3 states, that's very cool. I like it. Simple parity neighbor checks in P1, BFS on top of that P2, and same P3, but with 3 rotated variants of the grid. Okay, perfect. Yeah, that's very cool. Yeah, I think, about the same as the other one, I presume. Yeah, again, because if you know you're working top down, left or right. And again, I guess you can do this, you know, is it divisible by 2 type thing, and that will tell you whether you're up or down, and so whether you look up or down. But obviously you have like side forward and backward. When I was solving it, it felt very natural to try and like treat the triangle itself as a grid, and that allowed me to like I think it makes my neighbors function a little nicer, but not too hard, not too easy. Yeah, I kind of agree with that. I mean, I was never going to get the last part. Maybe I would have if I had kept sticking to the math, but it was getting late, and I'm like, you know what? I'm just gonna try and figure this out with the help Okay, there's still not a lot of solutions, and I think it's just because I've solved it the same day, and clearly, like, they're, I would say, generally better than me, but like I think my it sound like I placed in a similar position, or maybe that was just the points I got. 90th. Okay, so it's not that far. But the idea that, I think this person's probably gotten some really low scores before. Uh, I think it was a harder day, especially the part three. I definitely think you could do part one and part two. The translation rotation part is a little weird. Even if you say to yourself, "Oh, I'm just gonna rotate it around," um, or I'm gonna have like three like states of the grid, and like move between them. Probably to, I mean, that's enough math that you really got to think that through, right? Maybe I'll try and do it that way just so see what it looks like and make a comparison. But the fact that you can, again, that the thing that was intuitive to me was to say, oh, I don't have to rotate the grid, I just have to rotate myself on the grid. I can just like move myself around, and it's an, I guess these other things is like once you've moved the grid the three times, it's an O of one operation, right? You're just moving one grid state to the other. But this is the same too, right? It's like O of one. I can just teleport myself to one spot. And so I suppose if you don't know about this, and technically I didn't, I had to look it up, right? But if you don't know about this, thinking about the rotated grid probably is easier. And that might be worth understanding how you do that thing. So maybe I'll add it to do this because it might be worth looking at. Is like do how might, because it might be fun to talk about that. Just okay, there you go. That was a lot of fun. I enjoyed these days. Um, and I mean, just in general, everybody codes. I love solving problems, and I had not heard about everybody codes. I guess it's just 2 years out. They do have a couple stories that are like mini series, I guess, that you go through too. And those, I think I've done one of them. Have I done? Like, I don't think. But anyway, those are a lot of fun too. So, um, I think it's cool that we have more people creating puzzles like this. Like I do Sudokus as well sometimes, and I think it's cool that there's a community around building puzzles and then people solving those puzzles. We have a lot of people that like to solve puzzles, but not a lot of people who like to make puzzles. Or at the very least, people I it's hard for me to find places where we find these types of puzzles, right? So these are interesting puzzles. Obviously, like caddis problems and competitive programming problems are interesting, but they aren't these type of puzzles where you're like telling a story and going through, a flow of, you know solutions and building up to things and stuff like that. So it's fun to have those. It'd be cool to have more puzzle makers for the puzzle solvers, I'm sure. So if you have an inkling to make puzzles, and or where other people are making puzzles besides everybody codes and advent to code, I'd love to see them. It would be fun to go and through them, try and solve them. So yeah, that's the end of it. Well, I'm sure we'll be back for next year. It sounds like they're going to do it earlier in the year, the last I heard. So we'll do some more everybody code. But so, like, if you're wondering what's happening with the rest of the channel, we'll next week advent to code starts. So the next videos you see will probably be advent to code. Again, it's reduced. It's only 12 days. So it'll only be, we'll only have like 12 days of that, but it will be like 12 days in a row. I don't know how far ahead or behind I'll get. Usually when it gets to the holidays, it's hard. But also sometimes weekends can be difficult for me, just depending on, sometimes weekdays are easier, sometimes weekends are easier. It rotates. But I'll try and do a video, 5 videos a week or something along those lines. 5 videos a week, if not all 7 for advent to code. Then once we get done with that, we got lots of more puzzles to solve, right? More Advent of Code. We got several years of Advent of Code that I'm like resolving. And we can go back to solving the unsolved everybody codes, including some stories that I've already solved some of those, so it'll be reviews like this. And then, you know, Caddis always has some. But if you have other puzzles that would be fun to solve that you think I would enjoy, I'd love to hear it. So send them my way, and I'll give them a shot. Okay, I think that's it. Thanks everybody. It was a fun year for everybody's codes. Talk to you next time. Advent of Code. Bye.